Alright, so now let us start the next chapter, what is called inner product spaces for us. So we are going to study what are called inner product spaces. So in school we had learned what is called the dot product and the vector product. It turns out that vector product cannot be generalized at a higher level because of certain restriction. It was possible only in 3 dimension, nowhere else. But dot product can be generalized for anything. And the idea of dot product was, let us try to understand, we could talk of angle between 2 vectors, angle between 2 vectors could be discussed, and this also helped us to look at x dot x and then a square root of that, which was, if I write x as x1, x2, x3, then x dot x was x1 square plus x2 square plus x3 square and a square root. So we could talk of this, which was called the length of the vector. All right, fine. So we had 2 ideas. One was the dot product gave us the angle as well as the length of a vector, and the angle between the vector was given by cos theta, which was x dot y divided by length of x into length of y. All right, this is what the idea was. So what we want to do is that we want to generalize these ideas, because these things are meaningful when I am looking at R2, R3, but if I want to discuss angles on the, say, surface of the earth or moon or anywhere else, fine, or any figure which is not as plane as Rn, that is flat, I will have issues with me, because if I look at, suppose on earth itself, if I am starting from north pole, all right, I go south, go east, again go north, all right. So what I am saying is that I start from north pole, go south, east and north. It turns out that I reach north pole itself, fine. But in Euclidean plane, if I go from any point to south, east and again go north, I will get to a parallel place, not to the same place, all right, fine. So therefore, the geometry on earth and geometry on Rn, they are quite different, fine. So we will have to define these things depending on the requirements, fine. So let us try to do things, at least for finite dimensional spaces, how should we go about doing those things, fine. So let us try to look at what are the properties of dot product, properties of dot product. So recall what we had done for vector spaces also. What we had started was we started the properties on R2 and R3 and took them as our basic requirements. That was the basic requirements, and then we defined things, all right. Similarly, whatever the properties dot products are going to satisfy, that will be our minimum requirements. So what are the things? Recall, x dot y was same as y dot x. Then we had x dot y plus z was x dot y plus x dot z. 3, alpha x dot y was same as alpha times x dot y, which was also equal to x dot alpha y, fine. And the 4th was related with the distance, sorry, not the distance, this length, that x dot x is positive for all x not equal to 0 and x dot x is 0. So in some sense we are saying this itself, all right, fine. So this was the minimum property of dot product that we followed in our school, that is, the dot product is commutative, it distributes over additivity, then there is a notion of scalar multiplication for vectors, so it behaves nicely with scalars, and then the length is always positive whenever the vector is non-zero, fine. So we take it as our basic requirements for our inner product. So definition of an inner product, definition, let V be a vector space over F, all right. There we looked at things over R2 and R3, fine. Here also we are looking at over F, so we will be looking at Fn in some sense. So V for us. So then a function So there is a different way of writing is denoted this from V to F is called an inner product or dot product if 1. So this is the way we write. We don't write F anymore, we write like this. So what we are saying is that x comma y is same as y comma x for all x y belonging to V. All right. So the first property was commutativity of x dot y same as y dot x. We assumed it as it is. Fine. I will make some changes to it after some time. To x comma y plus z will be equal to x comma y plus x comma z for all x, y and z belonging to V. 3. Ax comma y, we will write it as a times xy. All right. I am not putting it on the right, the last part. Here also I have done something, but not exactly the one that I require. Fine. So I will do that. 4th, which is important, is very important, is this part, the length. So what we are saying is that x comma x is greater than or equal to 0 for all x, and x comma x is 0 if and only if x is 0. All right. So the same thing that I wrote here, we are writing the same thing here. All right. Now the only thing is that if I am over real numbers, everything is nice, this definition is fine, but our syllabus also requires us to understand a little bit of complex theory, and therefore for complex numbers I need to talk of complex conjugate, and therefore the first one gets replaced by a bar here. All right. So we look at this bar that is important for us as far as complex conjugate is concerned, and therefore because of this complex conjugate, what happens is that if I want to look at x comma ay, fine, it will turn out to be, just look at this part here. So this will turn out to be ay comma x whole bar. This is what the bar definition was, which is same as, now if I go with this part, this definition, the first component, I can take out a from the first component. I am not talking about, if I look at this definition, there is no talk of taking out a from the second component. Fine. So now I can take out a from the first component, but here it is with a bar. So it is a times yx whole bar, which is same as a bar yx, which is same as a bar of xy. Fine. So when I am taking out a from the scalar from second component, I get a bar into play. Is that okay? So this is a bar that is playing the role. So you have to be careful. If you want to take out a scalar from the first component, it comes as it is. But if you are taking out from the second component, the bar comes into play. So this is the way we define. That's the definition. All right. Definition. And let me give some examples first, and then go into it. The example. First example, our dot product itself. So we define, so in Cn, all right, I take x and y belonging to Cn. I define x comma y as y star x. So x here is some x1 to xn, y is y1 to yn, they are complex numbers. All right. So therefore this will give me y1 bar till yn bar times x1 to xn, which will be nothing but x1 y1 bar plus x2 y2 bar plus xn yn bar. So you can check that the first condition will be satisfied, second will also be satisfied, because just look at the second part. So first is satisfied first by definition itself, because xy is y star x That's the way we have defined here. Fine. And if I want to look at yx whole bar, this by definition will be equal to, so this will be equal to bar of yx is nothing but x star y, because star is coming from the second component, all right, second component. Fine. So which is same as taking a star, because it is a scalar quantity, a scalar. So it is same as looking at x star y whole star, which is same as y star x star star, which is y star x, which is same as by definition is xy. So you can check that first condition is satisfied. Second condition, x comma y plus z will be equal to y plus z whole star x, which is same as y star plus z star x, which is same as y star x plus z star x. Fine. By matrix multiplication. Fine. 3, verify it yourself, 3, verify. Fourth one, let us look at x comma x. So x comma x will be x star x, which will be equal to mod of x1 square plus mod of x2 square. So mod of xn square, which you know is always greater than equal to 0, and equal to 0 if and only if xi is 0, which is same as saying that x is the 0 vector. All right. So you can check that everything is nice. You are able to get things as per this definition is concerned. All right. So if this definition is there, everything is nice. Fine. So let's go to the next definition, next part. Another example. Example 2. So define this in R2 by, so in R2 I have got vector say xy. So x is x1 x2, y as y1 y2. I am defining my this as y transpose ax for some matrix A. All right. I want to check. So aim to find conditions on A such that this defines an inner product. Fine. So for example, if I look at example, for example, if A is identity, then x comma y is y transpose x, which is nothing but the dot product. All right. So what we are trying to do is that we are trying to generalize the idea of dot product. Fine. So let's take another example to see that whether it can work or not. So what are the conditions we need? The first condition we need is, all right, conditions that xy should be equal to yx bar. Fine, which is same thing as saying that xy is y transpose ax, and I am taking A to be again real. So A has real entries. I can take them as complex entries, but since I am looking at R2, I am looking at real entries only. All right. So y transpose ax, so it will be yx is x transpose ax, x transpose ay, bar of this. Everything is real, so there is no complex conjugate, which is same as x transpose ay. So what we are seeing here is that we have got y1 here, y2. Let me write A as A, B, C, D, fine, times x1, x2. I want this to be equal to, look at this part, x1, x2, A, B, C, D, y1, y2, fine. So this tells me that, just multiply it out, A times, multiply this into this, ay1 plus cy2, by1 plus dy2 times x1 x2 is equal to ax1 plus cx2, bx1 plus dx2. Please verify because I do lot of mistakes. All right, I am very good at it. So you have to spend time and verify things. Is that okay? So this is same as a times x1 y1 plus c times x2 y2 plus b times c times this into this. No, so there is a mistake here as usual again. So I am multiplying x here, so c times x1 y2 plus b times y1 x2 plus d times x2 y2. Here it is equal to a times x1 y1 plus c times x2 y1 plus b times x1 y2 plus d times x2 y2. Now this has to be true for all choices of x1 x2 y1 y2. Since this has to be true for all choices, fine, you can see here that this and this there is no problem. Similarly this with this is no problem. The problem is here. Here it is c times x1 y2, whereas it is here c times x2 y1, and it is b times x1 y2 and b times y1 x2. So just match it. C times x1 y2 he is here, where it is x1 y2 is coming with b and this is coming with this part. All right. So if we take, if we take b is equal to c, then we get that xy is indeed equal to yx. All right, for all xy belonging to R2. Is that okay? So therefore we need that the matrix A, the first condition requires us that the matrix A has to be symmetric. Fine. Condition required. A has to be symmetric. So let us write A as A, B, B, D for us. Fine. And proceed further. Now, so once this is done, then you can check that second condition is valid as well as third, because x times y plus z will be equal to y plus z transpose Ax, which by matrix multiplication will be y transpose Ax plus z transpose Ax, which is xy plus xz, and third part will also be valid. All right, so check it out, valid, no problem. Fine. Now the problem is with the fourth part. We want that x comma x should be greater than equal to 0 for all x not equal to 0, and equality if and only if x is 0. All right, this is what we want. So let's compute that part. So this gives me x transpose Ax, which I would like you to see that it is nothing but A times x1 square plus 2b x1 x2 plus d times x2 square. All right. So therefore, if x2 is 0 and x1 is not 0, will imply that x2 is 0 means this part will be 0, this part will be 0. You will get only left out with a x1 square. You want this to be greater than 0 for every x which is non-zero, and therefore a has to be positive. All right. So this gives me a condition that a has to be positive. Fine. Similarly, if I take x1 to be 0 and x2 to be non-zero, it will imply that d has to be positive. All right. So the diagonal entries are positive. What about the determinant? Can I say that determinant is also positive? All right. So question: do we need the determinant to be positive? All right. So let us try that out. Fine. So I already know that a is positive, d is positive. So let us try to do what is called completing the square. So x transpose Ax by for us is nothing but a times, so a times x1 square plus 2b upon a x1 x2 plus d upon a x2 square, which is same as a is outside, x1 plus b upon a x2 whole square. Just let's check whether it's okay or not. x1 square plus 2ba x1 x2, yeah, fine, plus d upon a x2 square minus a square coming from here, which is b square by a square x2 square. So this is a times x1 plus b upon a x2 whole square plus x2 square common, so x2 square by a square common. I get here ad minus b square, ad minus b square, all right, fine. So now what I want is that this has to be greater than 0 for all x non-zero, all right, fine. So if I take x2 to be or x1 to be minus of this part will be 0, fine, and therefore I need that this has to be positive, all right. So if I take x1 to be equal to minus b upon a x2, this part is 0, so I will need that need, and x2 not equal to 0 will imply that ad minus b square should be positive, fine. And what is ad minus b square? Our matrix was a b b d. This is nothing but determinant, fine. So we need that a has to be positive, d has to be positive, and the determinant has to be positive, fine. Such matrices have a special name, they are called, so a matrix A n cross n, symmetric and satisfies A of SS 0. So recall that, what was that? This was the determinant of something, all right, positive. Or for the 2 by 2 case, we just need that. So A is 2 cross 2. We need A has to be positive and determinant of A is positive. In general, I need this to be 0 for all S, a subset of 1 to n. All right, this was the determinant of S cross S submatrix. All right. We also had A of SS. So here it was in the chapter on determinant. This is what we had. This means remove the columns and rows from rows corresponding to elements of S. Corresponding to elements of S. Is that okay? So what we see here is that if I have got any matrix which has this form 2 cross 2, where A is positive, D is positive, AD minus B square is positive, then it is indeed it will give me a inner product. All right. So example, proper example, I take A as 4 minus 1 minus 1 4. Suppose I take, or say 2. I take this as my matrix. It is symmetric. So you can check that all the conditions will be valid here, and because 4 is positive, 2 is positive, this is this. So if I want to look at x transpose AX, which is for me going to look like x comma x, will be equal to 4 times x1 square minus 2 times x1 x2, fine, 2 times x1 x2 plus 2 x2 square, which is same as x1 minus x2 whole square plus 3 x1 square plus x2 square, all right, which is always greater than 0 if whenever x1 x2 is not equal to 0 and equal to 0 if and only if x is equal to x1 x2 is 0, all right. So you can check that everything is nice here. So we can ask questions here. So the questions that are going to come here, which can be asked, this question that let this be an inner product in R2 such that 2 comma 1 is inner product of, so inner product of two ways. So let me write x as 2 1, y as 1 3, all right, such that length of x, I have not yet defined what is length of x, but anyway, so such that x comma x is say 1, y comma y is 1, and x comma y is 0, all right. Find a satisfying above condition, all right. So what we'll have to do is that in such a case, we'll have to take a as a b c d, fine. Now x is 1 implies that 2 1 times a b b d times 2 1 should be 1. So this should be b itself because it has to be symmetric. So this will imply that 4a plus 2b plus d is 1. Just check it. 2 into 2 is 4 times a plus 4, I think 4b, not this, plus 4b plus d is 0. Please check all these calculations, all right. 1 3 I am saying here. So again 1 3 a b b d is equal to 1 will imply that times 1 3 is equal to 1 will imply a plus 6b plus 9d is equal to 1, and this part which is 0 will give me 2 1 a b b d times 1 3. 0 is equal to this will give me, just multiply. So 2a plus b 2b plus d 1 3 will imply that, so 2a plus b plus 3 दूना से 6b plus 3d is 0, or which is same thing as saying that 2a plus 7b plus 3d is 0, all right. So see here I have got 1 condition, 2 condition, 3 conditions, or 3 equations in 3 unknowns a, b and c. Solve it to get your answer, all right. So I would like you to try these out because they are important for us as far as the calculation is concerned. In the next example, next class we will look at some more examples here and try to relate different ideas, but most of the times we will be looking at only a standard inner product, all right. A standard inner product means just dot product itself. Is that okay? Dot product, or we will be looking at, where is that, so this part, or we will be looking at complex, which will be this part. Is that okay? So mostly we will be looking at this, what is the standard inner product. But we will look at some more examples, so for clarity, fine. That's all for now. Thank you.